Hey everyone, welcome to another episode of Science Man Says. In this episode I'll be talking about the production and the properties of an extremely strong diamond-like coating that can be applied to virtually any surface to increase its hardness. We'll start off by talking about this honeycomb-shaped molecule over here. And this is called graphene. It's a pretty amazing molecule in its own right. You could even call it a supermolecule. It has a wide range of promising uses in the field of materials science. For example, it's a superconductor under certain conditions, it's thermoconductive, it's chemically reactive, it's flexible, and it's also ferromagnetic. For a long time it was pretty difficult to produce high volumes of graphene, but that's now beginning to change. And that's because we have a production method called the confinement-controlled sublimation. And this involves a reaction with a different type of crystal called silicon carbide. Silicon carbide is a really common material for use in high-performance items, such as ballistic vests, sandpaper, electrical resistors, and LED lights. To produce graphene from silicon carbide, we have to place the material in an imperfect vacuum container to make sure there's a constant suction and heat it up to around 1600 degrees Celsius. This high temperature causes the silicon atoms, and only the silicon atoms, to be removed from the top layer of the crystal, leaving the carbon atoms behind. This eventually leaves us with just a layer of carbon, which for the most part is able to arrange itself into a sheet of graphene, just like magic. Researchers from the City University of New York were actually able to grow a double layer of graphene using this method to produce an extremely hard surface, which is close to and sometimes even harder than diamonds. And this can be used, like I said before, as a coating for virtually any object. So how have they achieved this wizardry? Compressing them together, applying around 1 to 10 gigapascals of pressure. So we start off with these two superimposed layers of graphene, and there's no interaction between these two levels. So basically what you have to know about carbon is it has two different types of energy levels, two different orbitals. The S level orbital, the lower energy orbital, which is where electrons orbit very close to the nucleus of the atom. A higher energy level called the P subshell, which is farther away from the nucleus compared to the S subshell. But what we have with carbon in this state is it actually undergoes a hybridization between these two S and P energy levels. And so under sp2 hybridization we have electrons from the S and the P subshell that actually merge together to create their own hybridized energy level. So under sp2 hybridization we have one S electron and two P electrons. And what that translates to is basically the carbon atom here is able to make 3 bonds with neighboring atoms. So looking at this 2D graphene molecule here, you can see that each carbon atom, each green dot, is able to form 3 bonds with a neighboring carbon atom. But what happens is when we compress the graphene, so we'll be applying around 1 to 10 gigapascals of pressure to it, it actually starts to zigzag a little bit. And that's because a phase transformation is occurring. So an extra electron from the P subshell is actually going into this hybridized energy level. So we end up with 1 S electron and 3 P electrons in this hybrid orbital. 4 bonds can now form between neighboring carbon atoms, and the shape that the molecules take on is something called a tetrahedral, which is sort of what's illustrated over here. And what's caused as a result of this sp3 hybridization is that bonds form between these two layers of graphene along the z-axis. And that's what gives it its diamond-like structure. The thing about this diamond-like structure is it's actually more closely related to a rare type of diamond derivative called Lonsdaleite, which can actually be around 60% harder than diamond. So why don't we just use more layers of graphene to make a material that's even harder? Well, unfortunately it doesn't really work that way. And researchers found they actually couldn't get more than 2 layers to align together well enough to form this diamond-like structure. This was confirmed when researchers tried to press on the layer itself, and they found that the indentation that was made was actually a lot larger than if there was nothing there at all. So looking at this force indentation graph, we can see that applying a force of 20 nanonewtons causes different levels of indentations in each of our 3 different materials. When the force was applied to our 2-layer graphene, an indentation of around 25 picometers was produced. Whereas if there was no graphene there at all, the indentation would be twice as large, at around 50 picometers. And if we put a very large, very thick 5-layer graphene on top of the silicon and compressed it using 20 nanonewtons of force, we actually get an indentation that is around 3 times as large as the 2-layer graphene, so around 75 picometers. So as I mentioned before, this decreased performance was due to the fact that more layers won't align well enough to produce that diamond-like crystalline structure. Alright, so that's all for this video. I hope you enjoyed it. If so, please leave a like and consider subscribing, and also leave a comment if you have any questions or if you have any suggestions for a video. I really appreciate it.